we can get started with the first keynote, which will be done by Oisin and showing the screen now. And just quickly, so Oisin is a lecturer in machine learning in the School of Informatics at the University of Edinburgh. From 2016 to 2019, he was a postdoc in Professor Pietro Perona's Computational Vision Lab at Caltech. Prior to that, he was a postdoc in the Department of Computer Science at University College London with Professor Gabriel Brostow and Professor Kate Jones. He received his PhD from UCL in 2014, advised by Professor Gabriel Brostow, and has an MSc in machine learning from UCL and a BEng in electronic and computing engineering from the University of Galway. Along with being a fellow of the Alan Turing Institute and a European Laboratory for Learning and Intelligence Systems scholar, his current research interests are in the areas of computer vision and machine learning, with a specific emphasis on shape and depth estimation, human-in-the-loop learning, and fine-grained image understanding. So thanks, Oisin. The stage is yours.
Great. Yes, thank you so much, Jamie. As Jamie said, my name is Oisin. Normally, I have to start my talks spending 2 minutes describing how to pronounce my complicated name, but actually, Jamie did such a good job. I can save 2 minutes on that, which is great. So, yeah, it's great to be talking about this topic. It's something I'm really excited about and interested in. So, thanks for giving me the opportunity to do that, and thanks for allowing me to do that remotely. I definitely would like to be in Hawaii instead of slightly rainy and miserable Edinburgh, but that's the way it is. So I'm going to attempt to kind of just cover some old work, some more recent work today, and then maybe spend more time at the end kind of highlighting what I think are some limitations of current approaches to self-supervised monocular depth estimation. So I think if there's a smaller crowd, I'm totally open to questions. So if people want to put questions in the chat, or I guess if people are in the room and Jamie wants to relay them, don't hesitate, because I'm very happy to spend more time on that than just kind of going over some of the papers as well. So please don't hold back. Great. Okay, so I don't need to explain what monocular depth is, but I think if people here will know that. So if I was fortunate to be snorkeling off the coast of Hawaii and I took this photograph, in terms of the monocular depth task, what we'd like to be able to do is estimate the depth for each pixel in the image. So that should look something like this. Where in this color coding, brighter colors mean that the objects are closer to the camera, and darker colors mean that they're further away. And so there's different flavors of monocular depth estimation. It could be that we have actually a metric depth, and so those pixels actually encode this color coding actually codes something like depth in meters, for example, or it could be that it's up to some unknown scaling factor, for example. So is monocular depth useful? I guess I think it is, and probably most of you hopefully do if you're here at the workshop, but we can kind of go over some of the classic applications of it. So there's applications for tasks such as interaction and generally in perception. So this is an example from human-computer interaction. And so monocular depth, you could imagine, would be particularly useful in settings where maybe it's not possible to have a kind of a bulky kind of LiDAR sensor like you would have in the case of a Connect2 style device, or maybe like a multi-camera setting is also even too either expensive or the form factor is too much. So monocular depth could give you that signal potentially with just a single camera, which would be great. There's applications in photo editing. So for example, if you took a photograph and then after the fact, you were able to estimate a plausible depth or structure for that scene, and you can then go back and actually relight that photograph. So this is a nice example from SIGGRAPH Asia from a few years ago. You can virtually relight this scene, even though you just had a single image taken. There's more recent examples, which I think are quite cool. People probably have seen this as well. So this is from the latest Stable Diffusion release. So they have this depth conditioned image synthesis. So the idea is that we now have these powerful generative models, but we can condition these models either on images and get outputs that are contain similar semantic content, for example, or similar structure, but we can actually also condition these models on depth. And so in this case, this is estimated depth from a supervised depth estimation model. So the input in some sense to this model would be these two inputs here. And then the output would be synthesized outputs, and we can decide how much we wanted to just utilize the structure, the shape or the depth information, and how much we also wanted to use the appearance information. But this is a really great way to be able to generate variations on an image while keeping some elements of the actual fundamental structure of the scene constant. And there's a nice example here as well, which I saw recently. So again, the example is that as an input, we have this little scene with these kind of toy pieces of furniture. And this is the estimated depth, again, probably from Midas. And then when you generate some outputs using something like a stable diffusion style model, it depth condition one, it respects the depth structure of the scene, but it generates different appearance variation. So you can see the bed, for example, and the objects are all in a similar position in the scene, but the appearance is widely different. So this is quite a cool tool and use case for depth. The other classic one is obviously augmented reality. So hopefully these videos are playing reasonably smoothly. But on the left, we've got an augmented reality situation where we've got this little virtual Pikachu creature running around. And here we don't have depth estimation. So the object, if you notice, is just kind of pasted on top of the frame. So it's never actually occluded by anything in the sequence. And as a result, it doesn't look particularly realistic in terms of how it interacts with things. Still running on a ground plane, so it looks okay from that perspective. But if we have depth estimation, like on the right, the object moves behind things. And so this is not perfect, but it definitely increases the immersion or the sense of kind of realism compared to the example on the left. Okay, so another situation that we found that depth was quite useful. This is quite a simple idea. So this is a paper from ECCV from a few years ago. So given a collection of images, just static images, single images, imagine a data set like Coco, for example. And what we can do is we can estimate monocular depth, again, take an off-the-shelf network and estimate depth for each image in that data set. Then from that, we can virtually render the scene from a slightly different viewpoint. So in some sense, what we're doing is we're synthesizing a stereo pair of images. And this obviously introduces issues because there's going to be pixels that become disoccluded, and there's going to be occlusion boundaries and so on. So there's some details for how to deal with that. But basically what you can do from this is you can generate your own stereo training data from single image collections. And so the advantage here is that now you can massively increase the amount of stereo training data you have and get stereo training data for situations maybe that are not available to you originally because you didn't have pairs of images for bears, for example. And then use that to either train or fine-tune your stereo network and actually improve the performance of stereo estimation. And so this is, again, like I say, a simple idea. People have also kind of built on this and done the similar things for optical flow and so on, but it's a kind of a nice way to utilize monocular depth to kind of close this loop again. Okay, so we've seen some examples of why it's actually useful, and now we can think a bit about how we actually go about generating depth from a single image. And the classic kind of pre-deep learning era was papers like automatic photo pop-up and Make 3D, and kind of to kind of caricature these methods, there were kind of local estimation-based methods and infusing those local estimates. So you can see in both cases, we start with an input image, we generate a set of superpixels, and then we're basically trying to estimate either the kind of orientation of those pixels or some coarse notion of depth. And then we've got some regularization that we want to employ such that neighboring superpixels have some kind of a structure that allows us to kind of capture the shape of these scenes, and these things that are typically trained on kind of supervised data in the form of LiDAR data, so trained locally. But for their time, these were quite impressive results, and I think really kind of motivated people to think more about what could be done in this task. So in the deep learning era, things got a lot, I guess, conceptually easier, even though maybe it wasn't trivial to do this in the first place. But fundamentally, what we have is we have an input image or a collection of images at training time. We have some neural network, which I guess is represented here by this arrow, and then we're just going to predict a per pixel depth. So we have a kind of classic UNet style encoder decoder model, for example, and we are able to train this thing end to end with supervised training data just through, for example, a squared error on the actual ground truth. And obviously there's a huge number of works in supervised depth estimation, and I'm not going to be able to do it justice at all, and there's great advancement in this space. But at its core, this kind of follows this recipe from Oisin from Europe's 2014 and follow-on paper, and which was kind of, an impressive result, I think, at the time. what we've seen late in terms of advancements in supervised depth estimation are works like MIDAS. So MIDAS obviously is a very well-known method and very popular. And the kind of key things that make MIDAS work is just having, again, some thought about how to actually structure your deep network, whether that's a conventional CNN or a transformer in the latest versions. Lots of supervised data, so diverse training data from different sources like, for example, 3D movies, but also conventional computer vision data sets and so on. So combined together. And then smart ways about thinking about how to combine those data, because fundamentally you've got different data sets captured with very different imaging devices with very different kind of depth scaling. And so without kind of being smart about how you combine that different source of supervision, you end up kind of suboptimally, in some sense, utilizing that signal that's available to you. And there's some nice tricks basically in MIDAS to be able to combine these diverse sources of data together. And then I guess also some nice priors in terms of regularization on actually enforcing very smooth depths, which I think is kind of a characteristic visual property of these MIDAS depths, that they tend to be kind of quite smooth in a good way in some sense, but also respecting intensity boundaries quite well. Okay, so what is the challenge here? So we've seen this amazing progress with supervised depth estimation, but it relies on having supervised training data. And as is probably well known, getting this data is not trivial by any means. Conventionally, this would have meant getting kind of these big, bulky sensors, LiDAR sensors, or kind of structured light sensors, and using them. And they obviously have limitations in terms of their operating abilities, whether that be the types of scenes. So maybe difficult to use them in direct sunlight, or difficult to use them where you don't have the source of power, but also difficulties in resolving certain types of materials, like shiny surfaces and so on. And so as a result, there's no real large online repositories of this data, and it's unlikely to imagine that we're going to get it anytime soon. Okay, so this motivated, obviously, a paradigm shift, which is how do we train these models without ground truth depth supervision? So how do we train from self-supervision alone? And so again, I'm only going to talk really about a few works today, and there's an amazing amount of work in this space, and it wouldn't be possible to cover it all in a whole conference worth of talks. But with that caveat in mind, what I'm going to do is just kind of touch on maybe some of the earlier works and then some of the things that we've been doing of late. Okay, so before I get into self-supervised training, let's just do a quick detour into stereo data in general. So in the context of stereo estimation, we have a pair of frames. So for example, you can imagine a left and right pair from a stereo camera system. And when we're collecting this data, we can obviously construct our acquisition rig so that we have a known intrinsics between those cameras, or at least we can certainly calibrate them after the fact. And we can also rectify those images so that the process of estimating correspondence for each pixel, so for each pixel in the left image, for example, because we have these images rectified and aligned, it's just a one-dimensional search problem to find the disparity or the shift basically as to where that pixel is in the corresponding, where its corresponding location is in the other image. And so if you think of this blue dot being the some part of this car here, once we have that correspondence, and because we know the baseline between the cameras and the focal length, we can actually use that to determine the depth of that point. And similarly with some other point there. So the kind of key takeaway here is that given a stereo pair, if we can solve the correspondence problem, we actually get depth from it. And so this was the key insight by a series of works back in 2016. So the most well-known is obviously Garg et al., but there's also Deep 3D, which maybe sometimes gets a bit overlooked. So Deep 3D was not pitched explicitly as a monocular depth method, but more as a 2D to 3D conversion method. And then we kind of followed up with the mono depth work just after these works. And so then to get a sense of what's happening, basically what we're going to do is we're going to train a neural network that's going to be able to estimate a depth for an image. And at training time, it has stereo pairs, but at test time, it'll only have a single image. Okay. And so the key insight is we treat this as a image reconstruction problem. So that's our source of supervision. We don't have depth to supervise it, but we do have image pairs. And so the idea is that if we can estimate the correct depth for a given image, we can use that to sample pixels from the other image in the pair. And if we have the correct depth and we sample them, the appearance of that sampled image should match the input. And because we're working with the stereo pairs, obviously the problem is simplified because there's no motion in the scene because the stereo pair is captured at the same point in time. Illumination effects and so on should be small. And because we have the kind of known camera poses or relative camera poses, this becomes a relatively straightforward problem. And so again, like I said, that's our training loss. And we can kind of imagine visualizing it in the sense that as we learn how to estimate that depth, the corresponding image that we generate should look more like the input because we've sampled correctly from the correct locations. It's obviously kind of a caricature of the whole process, but that's the kind of high level idea. Okay, so learning from stereo data is great because it doesn't require supervised depth. We just need the stereo data at training time, and we can do single images at test time. We can handle moving objects because basically we have to deal with them at training time. And it does, though, require temporally aligned stereo pairs. And inclusion can be a challenge because obviously in a stereo setting, there's going to be some pixels that are visible in one camera and not the other, and so on. So the next kind of development from this line of work was getting rid of stereo data at training time and just using single images. And so the kind of goal or aspirations here was to truly unlock the large quantities of video data that could be available. So there isn't repositories of stereo data, but there's certainly large repositories of single monocular video. And this would be a kind of an amazing source of self-supervision for these models. So again, in the stereo setting, we have these pairs, and for example, we might be capturing sequences over time. And in the monocular setting, we just have a single camera moving through a scene, for example. So fundamentally, the pipeline remains relatively similar. We have a source input frame at time t, sorry, an input frame at time t, and then we've got other frames, before or after, for example, in time. And making some assumptions about the world. So if we assume that the world is basically static, so the only appearance changes that we observe are induced as a result of the camera motion, and correspondingly, we also assume that the illumination of the world doesn't change from frame to frame. Fundamentally, the problem is the same. So we can estimate the depth at the current time point. We can use that to sample pixels from other points in time, and that's our source of supervision that drives ultimately the depth estimation. And the other change that we've had to make here is to introduce a pose prediction network. So we don't have calibrated camera poses anymore. We actually have to learn the relative poses as well between these different time frames. And so this was a kind of a big innovation by Zhu et al. And SFM Learner in CVPR 2017. And then we kind of followed on with this monodepth 2 approach, which kind of built on that and improved it in a few aspects. And so, yeah, this is our pose network. So again, it takes in a pair or multiple frames, and it produces the transformation between a pair. Okay, so again, these are kind of older methods, but just to give us a sense of where the trajectory looked like. So we basically have monodepth here, which is a stereo trained method, and we have a kind of okay results, but slightly blurry, and we have these kind of high frequency texture artifacts. The SFM Learner, which was trained on only monocular data, was kind of a breakthrough at the time, but it certainly was quite a blurry output for various reasons. And then the monodepth 2 method, which we followed up when, kind of leveraged the benefits of this, or certainly was able to train in this monocular video type setting, but resulted in much sharper predictions. Okay, so actually maybe what I'll do is I'll just glance through this really quickly because this is kind of slightly older stuff. So there's a couple of key innovations that monodepth 2 had to do. And so one of those things was dealing with occlusions between frames over time. So for example, we have objects like the wheel of the car here, the front wheel. It's not visible in all frames. And the problem is if we use that as a source of self-supervision, it's going to produce this kind of confounding signal for the model because it's not going to be able to find that wheel. And as a result, it's going to confuse basically this correspondence or this image reconstruction task. And so the traditional approach would have been to just, in some sense, attempt to find the match and just average this average this over multiple frames that you sample from. And the MonoDep2 approach was basically to only match the best, so this minimum reprojection loss. So in some sense, ignore the bad correspondence. And that gave us an element of robustness to this type of inclusion-disinclusion problem. Another problem, which is a big issue for anyone that's stared at Kitty for long enough, is this type of ego motion, or these objects that are moving at the same motion basically as the camera. So you tend to be following other cars and they're moving at a similar velocity to you. And as a result, effectively, the model can be tricked or fooled into thinking that these are just objects that in some sense don't change their relative scale with respect to the viewing camera. And so actually they can be represented quite well by in some sense, zero disparity, or this kind of like infinite depth. So just like the sky, they're just they don't change over time. And so this manifested as big issues in some of these older methods, because you ended up with these holes in situations at test time when you had objects that kind of appeared similar to the training ones when you were following cars. And so you had these big, effectively zero disparity, kind of infinite depth style errors. And the simple solution to this was basically to figure out how to capture those situations at training time and in some sense ignore those pixels. And so that calls for basically objects that are moving at similar velocity, like the car, or also just static things like the sky. So this is our estimated mask in some sense of what to trust. But also for scenes where the camera's not moving, because fundamentally, obviously, these monocular methods, they need motion, camera motion at training time. Great, and so in doing that, you can see that you can resolve these types of errors most of the time, a lot of the time. Let me skip this one. Okay, great. So learning from monocular video. Good thing it doesn't require supervised depth. Does not require stereo images, which is also great, just image sequences. We do have to have a pose network, but we only need it at training time. But it is more sensitive to moving objects, because we're making fundamentally some assumptions about the world, that the world is static, and obviously that isn't a particularly valid assumption in most settings. We do see some camera motion, some baseline to be induced by the camera, and then we also need some kind of well-behaved camera. So probably the secret of Kitty, methods trained on Kitty, is that basically the camera motion is pretty trivial. It's just this constant velocity moving forward and turning sometimes. So camera pose estimation problem is not particularly hard on Kitty. And so building on this work, we kind of, we were looking at this monocular depth estimation problem and thinking, okay, this kind of pure version of the problem where we just have static independent frames at inference time makes a lot of sense for like image collections like that you collect online and so on. But the reality of the world is that or certainly the reality of many applications is that you likely have multiple frames even at inference time as well, that you would want to be able to utilize in some sense in a smart way to make more improved predictions. So the question we set out to explore a year or two ago is, can we use information from multiple frames at test time when it is available? So again, the single frame depth estimation task is you just get a single frame, and through your network, you basically predict the depth, and that can be trained on stereo pairs or trained on image sequences. It doesn't really matter, but fundamentally at test time, you only make predictions for one image at a time. Like I said, the reality is there's many situations where we have a sequence even at inference time. And so we'd like to be able to utilize that information. So we'd like to make not just independent predictions at inference time, but we'd like to efficiently be able to make multiple predictions utilizing multiple frames. And so there's been a whole bunch of work over the years and still continues to be on this problem. So one set of approaches is that of test time refinement. So the idea behind test time refinement is do the same thing at test time you did at training time, which is a kind of a nice benefit of the self-supervised approaches. They don't need any depth supervision. So if we have a sequence of frames at test time, we can just basically do a small number of steps of gradient descent, for example, to update the parameters of our model to try and allow us to kind of fit to the test sequence. And so the problem here is that obviously this is a bit slow, and often some of these methods also use kind of future frames, which don't really allow you to do a true kind of online update. The other set of methods are ones that kind of used that use recurrent-based methods. So, for example, they have basically in the bottleneck of that network, they have some kind of recurrent network, like an LSTM, for example, or transformer, that utilizes information from the previous prediction and propagates that forward in time. So you're allowed to kind of share information from the past. And so the downside here, I guess, is that they don't explicitly really leverage any strong geometric cues about what you've seen before. It's just really kind of a black box application of those kind of time series models. And finally, the other way I guess you could kind of reason about this is more conventional kind of multi-view stereo, or specifically deep multi-view stereo. And generally the problem here is obviously these methods are kind of set up to handle static scenes. So it's more, the setting is typically a static scene with multiple observations for that scene. And then we integrate information into some kind of cost volume. And we and further process that cost volume to get a prediction of the depth. And so when the fundamental assumptions of the static world is violated, those methods are not going to work particularly well. Okay, so what we wanted to have was a model that could take a single frame as input and still do a monocular depth prediction. But the same model, the exact same weights, could also take multiple frames at inference time or test time when they're available and making a prediction. And actually improve prediction. So you can see in this example, it might be a bit small, but we failed to kind of resolve the detail of the pole. But in the example below, we get more detail here because we've been able to use multiple frames at test time. And so this is our mani-depth approach from CVPR21. And so it's self-supervised. It only requires video sequences of training time. It's real time in that it's only a single forward pass to generate depth. It works for both single and multi-frame input. So again, the same model can either do a monocular input or a monocular prediction or multi-frame prediction. And it produces depth for a static camera. So that's even when the camera is not moving. And so when this multi-frame information is not useful, we can still produce sensible predictions. Okay, so I'll kind of give a bit of a highlights for how this works, but I won't get into a lot of detail. So again, the classic monocular depth methods. Single input image, output depth. So in kind of inspired by these multi-view stereo approaches, we can introduce a cost volume here. So we can integrate features basically from different time points. And to be kind of pure about the online setting, we'll just integrate information from previous time steps at inference time. So we can integrate that into a cost volume. And so perhaps what was kind of interesting to us at the time was that we found when we did this, it wasn't particularly good. So the actual estimates were quite poor. And I'll get into this in a minute, but this was kind of perplexing at the time as, you know, we're adding this multi-frame information, we're giving it this strong structural geometric prior about the cost volume. So why is it actually doing a bad job of predicting depth in this setting? And so this kind of what we coined this kind of cost volume overfitting problem is that we inherit errors in the cost volume in our depth prediction. So in some sense, the model learns to overly rely on these poor cost volume predictions, and as a result, they kind of they spoil the predictions of the model. And so there's other issues as well that come as a result of this. I'm only going to talk about the first one today, really. The other issues is that we have, you know, these constant post estimation problem we're trying to do, and so there's going to be some unknown scaling factors as well that we have to take into account. And so traditionally cost volume based methods, they have these nice fixed bounds or min max depths on the cost volume, and so we have to be able to do this adaptively and deal with that. And they're also going to encounter test frames where there is no baseline, so the camera just has it moved from frame to frame, and we need to be able to deal with that inside of the same framework without the model kind of just producing nonsense. Okay, so like I said, the multi-frame system trained with the cost volume actually performed worse than the single frame model. And so again, the single frame model looked like this. And if we actually instead use this multi-frame network that had this cost volume in there, we've got these kind of spurious predictions. And we can also take a look at the cost volume itself. And this actually gives us a bit of insight as to why this was a problem. And I guess I'll look at that in a bit more detail on the next slide. So if we look at the cost volume, so again, we're building up this cost volume from just a sequence of frames. We can see that some of the fundamental assumptions that are needed are just violated in these kind of sequences with moving objects. So we've got moving objects here, which obviously result in spurious matches in the cost volume. We've also kind of got, maybe it's hard to see, like lens flare artifacts. We've got low texture reasons like the sky. So these are all kind of the worst case scenario for something like a traditional cost volume style matching. And they obviously then just kind of give us useless information. And so the question then is, how do we actually fix this? And so what we observe is that these single frame networks actually do, like the traditional monocular methods, actually do a decent job on moving objects. Not perfect, but they do a decent job. And so what we wanted to do was enforce consistency between a monocular style method and our multi-view one. And so basically, in a sense, we're trying to estimate some kind of notion of a reliability map that tells the model when to trust the single frame prediction. So this is a kind of a separate single frame network that we have available at training time. So we allow this to provide a consistency signal where the model knows when to trust this when it's useful, but then also it's able to conversely make use of the richer information that should come from the cost volume, or the more reliable information that should come from the cost volume when it is actually reliable. And so I'm not going to go into the details here, but you can think like the task fundamentally is to generate this this reliability mask that we use at training time, a bit like the auto masking loss and so on that we saw earlier, such that the difference between the single frame prediction and the multi-frame prediction is consistent. And as a result, this kind of significantly improved the performance. Okay, so just kind of giving some highlights of what those results look like. Basically, we have an input image here, and we ground truth depth, and then we can see the error maps from our conventional monocular method, monodep 2, and then comparing that to something like a LSTM-based approach that uses multi-frame information, or many-depth, which is much more efficient. And I guess perceptually, it's actually kind of a bit harder to tell the difference. But when we look at these error maps, we can see that there's significantly less red in the bottom row, which indicates that there's it's doing a much better job. So in some sense, you can think that at worst, in some sense, all it's doing is kind of fixing and correcting for these kind of nonlinear scalings that happen in the depth predictions, and giving us some minor improvements in some of the details. But that's actually resulting in a big improvement in the quality of the prediction of the depth, certainly when compared to the monocular method. And hopefully this plays okay over the video. This is just then a kind of a fused set. We basically fuse the outputs of the many-depth method and generate this kind of point cloud and just fly through this for a test sequence from Kitty. And you can see that this actually does a pretty good job of capturing the shape of the sequence. Okay, and so actually at WACV this year, we also have a paper that builds on this and applies the many-depth paradigm, or the many-depth model, to the task of 3D reconstruction. And so the problem setting that we explored was that of 3D reconstruction from a set of images. So given some images of a environment like a room, instead of learning to predict a full 3D reconstruction, if people are familiar with methods like Atlas or NeuroRecon, basically these are deep learning methods, supervised methods to reconstruct the 3D shape of a scene from image inputs. We instead opt for this lightweight representation, which we call a height field representation, which is a kind of a 2.5D top-down view of the world. So you can think that this is a top-down view, or predicted top-down view of the world, so the room here, or this environment. And so maybe these are chairs, for example, and tables and so on. And we can quite easily then just lift that into 3D. So this has the advantage of being a very kind of convenient or simple representation. We just have to store the height of each object, or the maximum height of an object at each pixel. And it gives us this nice kind of 3D prediction. The downside, obviously, is that we can't represent multi-height objects. Like we can't represent a table having a bottom surface and an upper surface, but that's a kind of a restriction of this representation. But we get this very compact output, which then can be refined by very simple 2D networks, as opposed to these very expensive 3D convolution methods, convolution networks that are needed for methods like Atlas and so on. So again, just to kind of give a very kind of brief highlight of how this works. So we have some scene with a bunch of cameras here, and we're going to assume that we have known camera poses. We get some images from each of these cameras, and then we're going to use our many-depth style network. In this case here, actually, this is trained with supervision. So it's the similar network as before, but instead of sub-supervision, we actually just do it with supervision, just basically to be able to compare more directly to things like Atlas and so on. And it produces depth estimates for each of the frames, but also we get features for each of the frames. And then we can fuse them into a TSDF. And so we have basically a kind of a conventional 3D reconstruction kind of fusion style approach where we fuse these depths into a TSDF. And then we can view this from above, which is effectively our raw height field. So it's basically the top-down view of this integrated 3D prediction. But similarly, we can also use the features from our 2D observations and aggregate them in a top-down view using the information from basically the estimated depth. And make this top-down aggregate features, and then make predictions, refine that prediction with this top-down network, which produces a final height field. So again, I've glossed over this super quickly, but the main takeaway here is that these kind of innovations from Monocular going to multiple depth estimation can be utilized inside of pipelines like full 3D reconstruction, and does quite a reasonable job at estimating the depths of these sequences. And so to give you a kind of a sense of what that looks like, so here on the left, we've got some input frames here from a subset of a sequence of some environment. Here's the ground truth 3D reconstruction, again, viewed from the top. And here is our prediction from our HeightRecon method. So again, it's a much sparser representation because it's just this height for each of these objects, but it's actually a pretty reasonable approximation of the shape and probably quite useful for tasks like navigation and so on. And so here in this little GIF, we just see an online reconstruction happening. So basically, we're kind of updating the prediction of the model online as it makes observations. So again, at inference time, all it gets is sequences of frames, and it has to estimate the depth and so on. So there's no supervision in some sense of depth provided at inference time. Okay, so I'm going to move on. So I think I've got 10 minutes left, or Jamie, you can let me know if that's not right. So what I wanted to do was kind of flag maybe in my mind what I think are some of the kind of current limitations preventing progress in self-supervised monocular depth estimation. So like I said, I've only been able to kind of do a whistle-stop tour of some of the kind of slightly older methods, and so there's new approaches that are attempting to address many of these limitations, but I still think that they're kind of valid and you know, important problems to try and solve. So one of the kind of big issues, obviously, is the limited data sets. So that means both training data sets and evaluation data sets. I had a look at the data set from this workshop, and I think it's a cool step in the right direction for moving away from this kind of kiddie-focused world. And in some sense, you know, we certainly need these types of data sets like that are being produced in the challenge. So it's great to see that being put out there. So, you know, Kitty has issues. I think people might be aware of them that have worked on this. So there's really limited appearance variation, limited kind of scene and shape variation, and quite simple scenes. Ground truth is imperfect, and so on. So it's got problems. We've got indoor data sets. They're more conventionally used by supervised approaches. And they also have issues. So, for example, MIU has kind of poor appearance. There's also issues with kind of low texture regions and kind of motion blur and camera moving and so on. So I think all of those things contribute to maybe some of the factors as to why this is a much harder problem to do monocular depth estimation, self-supervised monocular depth estimation from these types of indoor scenes. And obviously they have no you know, dynamic objects and so on. We've got other attempts to generate kind of supervised benchmarks like depth in the wild from human annotation. So this is relative depth annotation. So someone says that this green thing is closer than the red thing. And so they're varied because you can just collect any images off the internet and use those. But there's no video, so it's not useful for self-supervised training. It's manually annotated, so it doesn't scale very well, and it's just sparse annotation. But I think it's an interesting direction. And then there's other sources like multi-view stereo movies, and so on. So potentially very varied. Obviously, no explicit ground truth, which is a problem. There's also kind of other fundamental issues with 3D movies. So I mean, I guess there's one logistical one, which is there tends to be kind of licensing constraints, and so these data sets are not easily shared around. Also, the 3D that's generated, the depth is generated for a kind of an artistic effect, and so it's not necessarily metrically accurate depth as well. So that's problematic for it as a training source. But and it's also just fundamentally harder, I guess, to capture kind of stereo data rather than monocular data. So another kind of issue in my mind is that of generalization. So obviously it fundamentally comes from the lack of data in some sense. So we have models like MonoDep2 trained on kitty data, and that can generalize reasonably well to Google Street View imagery because it's a big flat plane and some objects on it. But when you try and run that model on indoor sequences, it just doesn't work very indoor images. It doesn't work very well at all. And so really this is a product of our lack of varied training data. Moving objects are definitely still a big issue. So, there's methods that have attempted to address it with semantic segmentation information or optical flow and so on, but it's still a big problem. And it's something that that we need to advance, I think, on these methods to be able to do it. But that's a kind of an exciting opportunity, and certainly has been for a while. Thin structures are also an issue. So again, it's getting better. We've got like HRNet and some of these methods that do a better job at kind of resolving some of this detail, but it's still fundamentally a challenge even for supervised methods. And that's something that, again, in this example here from a few years ago, it fails to kind of capture this nice thin lamp post or this tree, sorry, which would be, which is a shame. And temporal stability obviously is also an issue. So we do have multi-frame methods, like we said, and like I talked about, but still fundamentally we have kind of flickering. So this is a MonoDep2 result from, again, a few years ago, but fundamentally we have this kind of flickering, which is not ideal and kind of maybe obvious that we'll get that from these independent frame predictions. One thing maybe that is depending on if you're an optimist or a pessimist, you could say that it's a challenge that we've got to fulfill, which is basically realizing the potential of self-supervised learning. The other negative perception of that is that supervised is doing so well at this task, and something like MIDAS, does a really good job at estimating depth on a whole variety of scenes. It's not perfect, as we'll see in a minute, but self-supervised potentially unlocks this door open to kind of unlimited data that we could use to train and truly surpass the abilities of these supervised methods. But we're definitely not seeing that at the moment, and that's a really, I guess, in my mind, a kind of a call to arms to try and improve the performance of these self-supervised methods. So again, just to highlight these supervised methods, and this is relatively anecdotal, I've just picked out some examples where things fail, but these are examples from MIDAS V3. And it isn't perfect. It's kind of overly smooth, and so as a result, it misses these predictions, or sorry, it misses these holes on this object here. There's challenging scenes like this reflection on the water, and so again, that's just a hard thing to resolve, and something that is obviously an error in this case. This is an example from the data set from the workshop. This is situations where we have to make some decisions about what the use case is. So, for example, this is a prediction from MIDAS. So, should this be depth here? Should it take the glass into account, or should it be transparent? Maybe for robotic navigation, we want the depth to represent the distance to the surface. Maybe for augmented reality, we want to be able to see through it. So again, there's a whole bunch of kind of questions here that that need to be resolved in terms of how we deal with these more complex types of scenes. Great. So I think in my mind, that's kind of the main invitations. I probably missed things. And so I'm definitely interested to hear what other people have to offer in terms of that, or maybe people think that we've actually got a long way to addressing some of those problems. I think I'm very open to being corrected with some of that. Big thanks to all these people here, Clement, Jamie, Michael, Gabe, and Sarah, who worked on various projects here, and some of them provided slides as well. So thanks for that. And I've left my contact details here in case anyone wants to follow up with any of this stuff. But otherwise, thank you very much for the invitation, and happy to take any questions as well.
Great, thanks, Oisin, for that great talk. Really, really interesting stuff there. So yeah, if there's any questions from the audience in person, I think there's a mic that we can try it out, see how well that works. If not, I'll just repeat the question if you can't hear it. Okay, could you hear that question?
Unfortunately not. No, maybe you could repeat it.
Yeah, okay. If you want to ask the question, and I'll repeat it.
In particular, has anybody worked on domain adaptation? Where things are supervised, let's say, for autonomous starting at the ground, and then you test it with the drones in the air.
Right. So the question was related to monocular depth estimation for more like drones and unmanned vehicles, and also potentially the idea of using domain adaptation where you have models that might be trained on these more, vehicle type of viewpoints, and then how can we maybe adapt that to work from these, different style of viewpoints.
Yeah, I mean, that's a great question. I think, I guess we've seen parallel work, which is basically the sim to real style adaptation. So there's certainly a lot of work on domain adaptation and domain shift in this problem. I think that specifically that drone scenario, I can imagine it introduces its own set of problems. Like you have cameras moving incredibly quickly, so we're going to get a lot of kind of wobbling effects in terms of visual artifacts on the frame, and there's going to be a lot of motion blur and so on. So I'm guessing there's going to be visual properties of those types of images that maybe are just very hard to capture in a more kind of well-behaved on the ground setting. But I certainly think that there's value in being able to highlight a whole bunch of these types of applications, so we truly can get monocular systems that can work well on a whole bunch of thoughts, whether that be medical or whether that be drone or whether that be indoor scenes and so on.
Cool. And I think we have another in-person question. So yeah, I'll just repeat that in a moment.
Yeah. So nice talk. I'd like to know your opinion on the potential of applying neural radius field in the supervised or assistance. Because in the case of neural radius field, we can separate a meaningful set of background. During the probably we can avoid effects of pedestrian, for instance, in the training.
Right, yeah. So the question was about how, if we could leverage neural radiance fields to deal with some of these problems where we have dynamic objects and separating those from the background and using that for supervision. Yeah.
Yeah, I mean, I think there's clearly, obviously, a lot of value these types of new representations, like nerve style representations, could potentially bring to the problem. Obviously, they have their cons as well. They're slow. They require multiple images, for a sequence. They don't right now work particularly well with dynamic scenes. But there's potentially a world in which, maybe you could do something like take a bunch of images of a scene, do a nerve reconstruction, use that as a kind of a pseudo ground truth, train your monocular method, and so on. I think that there's a world to be explored of how those things can interact, and we've already seen some papers that use monocular depth to improve nerves and so on. So yeah, I think there's some stuff that could be done there.
Cool, thanks. I don't know if there's any questions in the chat, but I actually had one question. Which is, so for example, in terms of the limitations, one of the big things we were talking about was data sets, which obviously, a lot of people just end up using Kitty, and we're kind of limited to these autonomous driving data sets. But then the other thing you mentioned is these problems, especially around thin structures. And so I was wondering, in the case of self-supervision, where do these problems come and how might we be able to fix them? Like, is it a problem with network capacity? Is it to do with the photometric loss being imperfect? Or like, what are your ideas on maybe how we can actually solve some of these?
Yeah, it's a great question. I think, these thin structures can be tough because often, it's the classic thing is like a telephone line or something like that, or some kind of wire, which really has very little kind of texture information to latch onto. But if you're flying a drone or driving around, you definitely don't want to run into those things. And so I think that I don't have a good question right now of how to deal with it. Certainly, we need fundamentally some element of resolution is a kind of core component. Whether that on its own obviously isn't the solution to the problem. We need then to be able to somehow be able to deal with that better at training time. Yeah, I don't have a good answer. Sorry, it's a bit of ramblings, but I think it's a good point, and it should be in some of our data sets. And it's maybe not. Maybe it is in your data set. I haven't looked. That would be cool if it was. You could really highlight that. But otherwise, it's a tough problem. Yeah, I see there's one question in the chat. Maybe I could really quickly read that one, unless you want, and then we can move on. So Rich asks, the problem we often have are with thin structures, but also with the sharpness of depth discontinuities. We often see smearing of the depth of these sharp depth continuities. However, on your kitty fly through where you were rendering points as a colored point cloud, didn't seem to have any smearing. Did you do any additional cleanup through the artifacts? Yeah, there's a bit of cleanup and stuff going on in those kind of situations to kind of quickly pull that up. To basically resolve these multiple predictions and so on. So this is kind of like not an online estimation, but basically after the fact. So, you know, yes is the short answer, but because we're using this kind of multi-frame style approach, we do get a kind of an improved depth, which does reduce a lot of this kind of smearing and so on. But if you do look hard, you see kind of fine pixels and all the usual stuff that does end up there being there. But again, the advantage of being able to kind of integrate loads of predictions after the fact to make a reconstruction like this is that you can use kind of techniques to get rid of some of it.
Yeah, I think so. Yeah, I think we'll do one more question. Again, it's from the audience here in person, so I'll just repeat that out.
Okay, Catherine. My question is, most of the metrics, I think, are relative, and I'm wondering what the state of the art is for quantitative depth estimation, which is needed for tasks where you're actually driving more robotics, and whether the use of relative metrics is kind of dives toward content creation kinds of applications where you have to be task scale, and what's the prospect for self-supervision for pretty much any scale.
Right. So the question was related to the fact that a lot of these depth estimation models actually tend to produce relative depth rather than metric depth. And so the question was how we might be able to create models, either supervised or self-supervised, that can predict this metric depth, given the fact that a lot of times if you're using relative depth, that's maybe more geared towards content creation, I guess kind of like the, was it stable diffusion generated, guided by depth, compared to applications where we do need that metric depth like driving.
Yeah, it's a great question. I think it's definitely the #1 issue we get on our GitHub page every so often. Someone will ask, how do I get metric depth out of this? Yeah, so I mean, again, it's an explored question, and there's a bunch of cool works that have looked at it. Again, one perspective is maybe this isn't such a bad problem, because if we want to utilize existing devices for pose estimation, we get pretty good pose estimation now with IMUs and so on. So we could get something approximating some kind of up to a scaled camera poses, which goes a long way then to improving the kind of calibration of our depth. The other perspective is that the world that we observe contains objects which we have pretty good priors on their sizes, and so we could just utilize that information to kind of to scale everything. So I think that scaling by offset by a factor is not such a big issue. I think we can resolve that. I think these kind of weird nonlinear scaling effects that we get, like where stuff that's further away is somehow scaled differently than stuff that's closer, that's a bit more of a problem, and that's probably a fundamental issue with the self-supervised methods themselves, and that needs a bit more attention, I think.
Cool, great. Well, with that, I think we can thank Oisin again. So yeah, great talk.
Thank you.